minute or so after. Welcome to everybody who is here joining us this morning. Our speaker today is Doug Edwards, well known to most of you. Doug may add on some of his experience, particularly as it pertains to today's discussion. He's going to talk to us about the practicality of heat pumps in Wisconsin. I find this a very interesting topic because I think that heat pumps originally got their claim to fame in the Southeast and part of the United States, and there was always a long feeling that Wisconsin was too cold a climate. And I hear from Doug, and I'm looking forward to his comments on how recent adaptations and improvements in heat pumps have allowed it to be used here in a colder climate like Wisconsin. So I'm especially interested in that point of view. So thank you in advance for coming and talking to us this morning, Doug, and you have the floor.
Okay. Well, I have to say that most of you know me, I guess, as just a member of this group. Actually, I've probably mentioned this before, that Richard really kind of inspired me to learn a lot more about nuclear chemistry than I ever knew before. I felt really at a disadvantage to him and several other people in the group, because I never really learned that much about nuclear chemistry. And I say that he inspired me because as a result of that, not only did I sort of work on my own to learn more, but eventually, or actually more recently, I've been taking a whole bunch of astronomy classes at the university. And that nuclear chemistry is very valuable when you're learning about astronomy.
Yes.
And I recommend, absent any discussion of heat pumps, I recommend to anybody in this group to take astronomy classes at UW. Just unbelievably interesting. Anyway, with that having been said, I'm originally I grew up in Maryland, but I went to school in Madison for my undergrad in chemical engineering, and worked as a chemical engineer for various chemicals and plastics companies. I went back to school and got a master's degree in chemical engineering at UC Berkeley. And eventually I switched over and I worked in finance for a little while. And during that time, I got an MBA at New York University. And then I moved into supply chain planning, and eventually that experience got me an opportunity to work for a tiny computer software company, which is what I did for the last roughly 20 years of my career. And I'm now happily retired. So that's sort of my background. And I'm going to switch over to this presentation really quickly here. Hold on just a second. And you guys should be able to see this now, I'm assuming.
Yes. Fine.
Great. Okay. So just a little background. Michelle and I have a place in northern Wisconsin. We happen to be in northern Wisconsin right now, believe it or not. And it is essentially right on the border with the the Upper Peninsula of Michigan, due north of Madison. So it gets pretty cold up here in the wintertime. And this house was originally built by Michelle's folks as their sort of a retirement place. They lived in Racine, and they spent a lot of time up here. And they built this house. It was a manufactured house that was put on a foundation here. Michelle's dad was a HVAC contractor during his career. And actually, I learned quite a bit from him about a lot of different things. But when he built this house, he put it in naturally an air conditioning system in, along with the forced air heating system. And so that sort of leads into this story about this heat pump, and it'll become more obvious a little bit as why. But first thing I wanted to get into was some of the background on a heat pump. What exactly is a heat pump? I don't know how familiar all of you are with heat pumps or air conditioners, for that matter. And so I'm going to go through some of that. Hopefully I won't bore anybody. If everybody knows about this already, we can skip through it. But I think it's actually worthwhile going through, because I know for myself, I knew quite a bit about it before, but I learned quite a bit more when I was researching this. And one other preamble to this, just so you know, one of the things that prompted me to do this was that I have a good friend now who works for WORT there in Madison. He actually lives right next door and started volunteering there. And he, along with a number of other people, co-host a radio show called the Perpetual Notion Machine. It's on Thursday, I think it's Thursday evenings at like 7 o'clock. And in a discussion that I had with him, I mentioned this heat pump business, and I had wanted to discuss with him some of the engineering aspects of it. And when I mentioned it to him, he said, "Oh, that would be the perfect subject for a radio show." And so I initially kind of reacted like I'm reacting right now, just laughing about the possibility of myself being a radio personality. And but I was always told by many people that I have the perfect face for radio. And so I took this on, and actually this presentation, really it was originally created, at least the basis of it was created for this radio thing. So anyway, most of us are at least a little familiar with air conditioners, and essentially an air conditioner, everybody knows, it removes heat from our living space, and we blow cool air inside and we exhaust warm air outside. And many of you may, I kind of intuitively, that heat energy generally moves naturally from hot to cold. And what an air conditioner does is it circulates a fluid or a refrigerant between a couple of heat exchangers in the air conditioning system. And the refrigerant, and now this is in an air conditioner, a refrigerant enters the outside heat exchanger hotter than the ambient air. So it transfers heat from the hot refrigerant to the cooler ambient air. And then the refrigerant entering the inside heat exchanger, the one that's in your air handler, by this time it's cooler than the indoor ambient air. So the warmer ambient air in the house transfers heat to the refrigerant, and that cools the indoor ambient air. In an air conditioning system, the warmer refrigerant coming from the refrigerant that's picked up heat from inside enters a compressor, and that increases its pressure, simultaneously increases its temperature, so that now its temperature exceeds the temperature outside. And I'll give you a diagram of this just a second. So, then there's the transfer of the heat from the refrigerant to the outside air passed through a special valve that drops its pressure, and when the gas drops its pressure dramatically, it gets very cold. Okay, so this is what an air conditioner looks like. So you may have heard, if you've ever, in particular, if you've ever paid to have one of these things installed at your home, you'll hear about the condensing unit. The condensing unit is a unit that sits outside, generally in an air conditioner. It's this thing right here, and you'll see that it's on the downstream side of the compressor. So this compressor is taking essentially cold, or I'll say, or cooler refrigerant gas, and it's compressing it. And when it compresses it, heats it, and it discharges that gas into the condenser, which is sitting outside. It's that unit that sits outside your house. And by this time, that refrigerant is at a higher temperature than the outside ambient air. And so it transfers heat to the outside. And during that time, you get a certain amount of condensation that takes place in that outside condensing unit, because you're cooling. You're removing heat and then cooling that refrigerant. So then that liquid passes down towards the inside of the house, and it goes through what's called a metering device nowadays. It's an expansion valve, and through this metering device, pressure is dropped dramatically. And when that happens, this gas expands, and when it expands, it gets cold. And that cool refrigerant then is passed into the heat exchanger that sits inside of your air handling unit inside the house. And so the air circulating in your air handler then passes over that heat exchanger, and this cool refrigerant, now this liquid refrigerant that's in there, is now transferring, or the ambient air in the house is then warming this refrigerant, which is liquid, as it enters the heat exchanger. And so it starts to boil that refrigerant in the heat exchanger and convert the liquid to a vapor. Okay. And then that vapor then transfers up to the suction of the compressor. Okay. And that's what the air conditioning cycle looks like. An outdoor heat exchanger, which is the condenser, and the indoor heat exchanger, which is called the evaporator. Okay. The other important elements of this thing include this metering device. And the metering device is, the way that it works is actually important in improving the efficiency of these heat pumps and air conditioners that we see today. And then this compressor. Okay, we're going to talk a little bit about compressor as well. Okay, so now that's what an air conditioner looks like, and I want to point out a couple of things here. So it's important with this, in particular here, with this evaporator, this heat exchanger that's inside the house, that the temperature of the refrigerant in this evaporator not be below, or even I'll say below, certainly 32 degrees. And that's because we have humidity in the house. And as we're blowing humid ambient air through this heat exchanger, if the temperature is below 32, we start to not only condense out water, but we also freeze the water, and we end up forming a large ice block that prevents airflow through the evaporator, through this heat exchanger. So the flow of the flow and the temperature of the refrigerant going into this thing is actually designed to run somewhere in the range of 35 to 40 degrees Fahrenheit. Okay. Now with a heat pump, imagine that now we're going to change or reverse these two heat exchangers. Okay, so we're going to reverse the flow of this thing. And we're going to put the condenser inside the house and the evaporator outside the house. And in this configuration, the refrigerant will actually absorb heat from outside, because we're going to put a very cold refrigerant outside, which will pick up heat from outside. And then we're going to exhaust the compressor inside the house instead, where that heated gas then will exchange heat with the inside ambient air, which is cooler than that refrigerant. So it turns out, and this was a comment that I made during this radio show, that it turns out that we can actually absorb somewhere between 2 to 6 times as much energy from outside and deliver it inside as we use compressing the refrigerant to get it to circulate through our heat pump system. And we openly called this a perpetual motion machine. So this is what the heat pump looks like when we reverse the flow. Okay. So now you see that this compressor is actually its flow is changed through a 4-way valve, so that this heat can act as both an air conditioner under some conditions when you want it to be an air conditioner, and a heat pump at other times when you need heat in the house. So there's actually a 4-way valve that is added to this system so that the system will act as a heat pump. And you can see that now the compressor is discharging to the indoor coil of your house, and that then becomes the condenser rather than the evaporator. Okay, and remember that the gas coming out of the compressor is hot, so it's exchanging hot air into the house. It then exits that condenser, and as that hot gas is going through the condenser, it's condensing the refrigerant that's passing through it. Okay, so you're removing heat from the refrigerant. It enters as a gas and then is condensed in the condenser. It then passes through this metering device, this expansion valve. again, what that does is it drops the pressure dramatically. When you do that to a gas or to a liquid, it will flash, and you'll get very cold gas liquid measure or gas vapor. Sorry, a vapor liquid mixture that then enters the outdoor coil now, which is going to become the evaporator. And at this point, this refrigerant is now colder than the outdoor ambient air. And it goes into this this heat exchanger outside, which is now your evaporator, and it condenses. It then starts to pick up heat from the outdoor ambient air, and it'll actually vaporize in this outdoor coil, this outdoor heat exchanger. And that vapor then enters the compressor again, okay? And then this cycle just goes around and around, right? So actually, what's kind of interesting is this is a picture that I found online of an experimental apparatus that would accomplish, it actually would allow you to determine the operating performance of both a heat pump as well as an air conditioning system. And this apparatus is actually the same setup as what we were just looking at. It's got two heat exchangers. It's got a compressor and an expansion valve. And it turns out with this, you don't need a four-way valve, because all we have to do is just switch these two buckets. We switch the temperatures of these two buckets, and this thing will act as a heat pump or as an air conditioner, just depending on the temperatures of whatever we put in these buckets. It's sort of an interesting way of demonstrating how this thing works. And you'll see here, this is the compressor right here. And then in this case, this is the discharge of the compressor. And the discharge is, boy, I don't screwed this thing up here. Now anyway, I think that this discharge then goes into this into a heat exchanger in this cold bucket, and transfers heat into here. It comes out of there through an expansion valve, and then down into the cold bucket, which is then going from which or rather the warm bucket, where it's going to pick up heat. Okay, and then it'll go back into the compressor. Okay, and then if you wanted to swap this thing around, you would simply swap these two buckets here. Okay, I think that at least from my perspective, this is a diagram that describes the thermodynamics behind what's happening in a heat pump or an air conditioner, for that matter. And it's called a Molière diagram. A Molière diagram is any diagram that has enthalpy, essentially energy, along the x-axis down here at the bottom. Okay, so increasing energy to the right. And in this one in particular, we have pressure increasing along the y-axis. Okay. And so we're going to start at the suction of the compressor, which is right here at 1. And you'll notice over here that if you take a look here, you'll see that the temperature isotherms run along these lines here. They come down, they hit this vapor liquid envelope, okay, right here. And everything in this envelope is a combination of vapor and liquid at various percentages, okay. And then at a particular temperature, let's see, you'll see that along this temperature isotherm, we come down here and we hit the envelope, and then as we move to the right, as we increase energy, the temperature stays constant, and that's what happens when you are when you're boiling something. Okay, it will boil at a constant temperature. As long as you hold the pressure constant, the temperature will remain constant as well as you're going through this vapor liquid envelope. And I think everybody can kind of intuitively understand this by watching a pot on the stove boil. It always boils right at 100 C at 212 Fahrenheit until the pot is empty, at which time the pot will heat up way beyond the temperature of boiling water. And if you lower the pressure, if you, for instance, you go out to Denver, say, you'll find that, in fact, that boiling temperature is a little bit lower because the pressure is lower. Okay, so as we lower the pressure over here, you'll see that the boiling temperature actually decreases. Okay. So again, we start here at the compressor and we increase pressure. And when we increase pressure, we actually move along. These lines right here are isoentropy lines, and a compressor is generally considered to be an isentropic device. And without getting into a lot of detail about that, just take me at my word on that. We move along this isentropic line, and we go up to a pressure that the compressor is designed to discharge at. And at that point, we're compressing. The compression ratio is somewhere between, say, 2 to, I believe it's like, well, in fact, in this case, it is, let's see, it's like 2.5. It's like 3 to 4 times. Okay, so your compression ratio is somewhere in the neighborhood of 3 here. Okay, maybe 3 to 4. And so you're going from a pressure of about 25, let's see, 2.5 bar, sorry, which is, I think it's about 40 PSI, something like that, up to, looks like 9 bar, which is about 270, say about 270 PSI. And in doing that, notice the change in energy, the change in enthalpy here along the x-axis. It actually it goes up by relatively little. Okay, so this is actually the energy that we're putting in that compressor in order to change this, to change the pressure on this refrigerant. And when we discharge remember that when we discharge this this refrigerant from the compressor, we're then going to pass it through a heat exchanger, and we're going to pass it through the condenser. Okay, so in the condenser, we're actually going to move left. We're going to move essentially at constant pressure, because the condenser tubes are sized in such a way that there's relatively little, if any, pressure drop through the as the refrigerant moves through the heat exchanger, the condenser, and so it essentially just moves left x-axis all the way over here to 0.4. Okay, and at 0.4, so we've gone through the we've gone through the vapor liquid envelope all the way, and we've actually then started to decrease. So we've condensed coming out of the we're completely in the gas phase. As we're moving left along this this horizontal line, we're condensing that gas, and then actually we've got a liquid over here at 0.4, and at 0.4 is where we hit that expansion valve. And you'll notice, okay, so we stayed constant pressure. Now we are literally going to just drop the pressure straight down. And when we do that, we actually flash this liquid into partially gas and partially liquid. Okay, but we are at considerably lower temperature. So notice that we just when we flash, started off in this case at 20 degrees. In this particular example, at 20 degrees centigrade, and we ended up down here at probably about -5 or something like that degrees centigrade. I'm going to say that's what that is, and maybe a little bit lower than that. That doesn't seem low enough to me, but in this particular example, this is the way this thing is running. And then we then put this after going through that expansion valve, we then pass this refrigerant through the evaporator. Okay, so here we are, we're picking up from the environment. This ends up, in the case of a heat pump, this evaporator is outside. So presumably we are now colder than the outside air, and we are picking up heat as we're moving to the right, all the way to the suction of the compressor again. So we've completed this loop, this cycle. We're back at the suction of the compressor, and we have now vaporized everything that we are pushing into the suction of the compressor. That's important because the compressor doesn't like to see liquid coming into its the suction part of it. So keep in mind that the energy that we put into this device, into this compressor, this energy between H1 and H2, okay? But the energy that we got out and we rejected into the house is everything between H2 and H4. So that the ratio between the difference between H4 and H2 and H1 and H2, that ratio is referred to, I think, in the HVAC world, the heating, the HVAC world, as the coefficient of performance of one of these heat pumps. And I mentioned earlier that that number varies between, I'll say about 2 up to 6. So you can get anywhere from 2 to 6 times as much heat out of this system as you put in energy. And that's kind of the secret behind heat pumps and arguably air conditioners as well. So air conditioners, again, they work exactly the same.
So Doug, what is that efficiency again? It's H4 minus H1.
Okay, so Lee, the energy that you're putting in is the only energy we're putting in, you remember, is right here at the compressor, which is going from 0.1 to 0.2. And so remember that the x-axis is enthalpy, energy. Okay, let's just call it energy. And so we're going from H1 to H2. That's the energy we put in. It's coming in the form of electricity that's driving this compressor.
Okay.
What we get out is everything that we exhaust or that we transfer in the condensing unit, okay, which is inside the house now. And that is everything from 0.2 over to 0.4, right?
Okay, right. Okay, and 0.4 is your expansion valve, and 0.1 is labeled as what again?
0.1 is the suction of the compressor.
It's the suction of the compressor.
Suction of the compressor, okay, the input of the compressor. And this is the output or exhaust of the compressor. 0.2. Okay.
And 2 is your condenser?
2 to 4, this, you know, right along this 0.3 here, all along in here is the condensing unit. Okay. It's condensing because you know you're going from vapor over here on the right to liquid over on the left.
Okay.
Okay. And down here from 5 over to 1 over, well, 5 over to really the suction of the compressor, you're evaporating this refrigerant. So this is always called the evaporator.
Okay.
And it's important if you're talking to an HVAC guy that you identify them that way.
Yeah.
Okay. Does that make sense to everybody? I'm not looking at your faces, so you have to give me some feedback.
Could I ask a question at this point?
Sure, absolutely, anytime.
It might be a little ahead of the game, but if I understand it, you don't want it to get the air too cold, the outside air too cold, you're going to have ice formation.
Okay, so we're actually going to get into that. It's a very good point, Richard, but you're a little bit quicker than I am.
Hold tight. Yeah.
Okay. Anything else?
Yeah,
okay.
go ahead.
I'm
Doug, yeah, go ahead, Richard. I'm sorry.
I was just going to say there's a I don't want to get too anticipatory, but you do that, I gather, by switching from dealing with air to dealing with water and coils of containing, not water, a liquid, which doesn't freeze. Is that basically
A refrigerant, you mean?
Yes.
That's what you're talking about with the refrigerant.
Yes, you're trying to get rid of something that would, such as water, that would freeze and mess up the system. So you're going to go to a refrigerant, but also we used to talk years ago about geothermal for temperate climates. And we use this old-fashioned term.
I'm going to talk about geothermal systems as well a little bit later.
You will. Okay. Yeah, I didn't want to miss that. Thank you.
Yep.
Yeah.
Okay, so
I got one clarification though. Doug, you're saying that there's 2 ratios you're comparing. And then one is H4 to H1 or H4 to H2? Oh, which one is that ratio?
Okay, so one of them is 2 to 4. Okay.
It's 2 to H2 to 4. Okay.
Okay, all the way there, because 2 is when the refrigerant comes out of the compressor.
Got it.
Okay. It's right here. Okay, so
Sure.
okay, so
Okay.
it's coming out of here.
So that's the denominator of your efficiency.
Sorry,
Yeah,
here's 2. They're saying 2 is right here. Okay, sorry.
You're on a different slide right now.
Yeah, I know I am. I'm showing
Okay.
you that this is the physical setup, okay, as opposed to the thermodynamic setup. Okay. This right here is the thermodynamics. Okay, this is what's happening thermodynamically in this cycle. And what I want to point out is that the energy that we put into this thing is the difference between H2 and H1. H2 is bigger than H1. Therefore, H2 is the outlet of the compressor. H1 is the inlet of the compressor. So the energy, the electricity that we put into this thing, the wattage that we put into this thing is H2 minus H1.
So that's
And
the
what we-
numerator of your efficiency equation.
That's the denominator.
That's the denominator. Okay.
Denominator, because that's what we're putting into it. Numerator is what we get out of it, which is all the way over here at H4 to H2. To see how much bigger it is. That's what I think is makes this intuitively so obvious a choice in pursuing. Let's put it that way. We're getting so much more energy out of this thing than we're putting into it. And where are we getting that? We're transferring it from the ambient air. We don't get it for free. In spite of my comment earlier about a perpetual motion machine, we're actually pulling heat from outside and we're going to deliver it inside. Okay. But to get that, all we have to spend in money is H1 minus or H2 minus H1. Okay. And we get out H2 minus H4.
So it's an efficiency that's greater than 1.
Well, the coefficient performance is somewhere between, that ratio is somewhere between, normally it's like 2 to 6. And I'll explain why it changes in a minute, but just suffice it to say that it's pretty significant, right?
Yeah.
Okay.
Okay.
You have to contrast that with, say, just using, for instance, electric resistance heat, where your coefficient of performance is 1 to 1. You're putting in as much energy as you're going to get out, right? In fact, you're going to get a little bit less out because you're going to lose some, you're going to lose something to other inefficiencies.
Mm-hmm.
Right?
Right.
Okay, so that's why this is essentially why heat pumps are. It's why they're putting them into electric vehicles. It's you're seeing them all over the place. Okay.
Yeah.
Okay, so with that, okay, so that's if you learn nothing else from this presentation, I think that's one of the most important things that you can take from this presentation is this picture of this Moliere diagram. Okay, that this is really kind of the secret behind heat pumps and arguably air conditioners as well. Okay, so next thing I wanted to do, and I'm hoping that this will come up. I won't swear to it. The compressor that's used. So I mentioned earlier that this pressure ratio here, it's important because we've got to drive the pressure up in the system. But remember that hey, we're compressing a gas to relatively high pressure. We have to design this thing to work within the confines of the materials that we're using. And you get the pressure too high in one of these systems, and the system will leak and maybe even fail. You may have a piece of tubing that fails, some weld fails, something like that, which is something that you don't want to have happen because it's expensive to fix it. So these systems are designed to operate within a pressure envelope, let's say. And this compressor that's used, I don't know if you've ever had to replace one in either your refrigerator or an air conditioning unit, but they can be, they're one of the more expensive pieces of equipment. And what's used in essentially all refrigeration equipment nowadays, and I won't say all equipment, but certainly any of these heat pumps, air conditioners, your refrigerator, your freezer, will be one of these scroll compressors. And I think, I'm going to see, I'm hoping that you can see this.
Congressman Derek Van Orden is selling us out while
Hold on just a
special
second.
interests cash in. He voted for tech.
Okay, so this is a, can everybody see this? Yes?
There's
No.
no video.
No,
What
no
I'm
video.
seeing is just, it says
It's just-
scroll compressor at the
Okay,
top.
I'm gonna run the
That's
video. I just wanted to
line.
make sure you can see it. Okay. So how does a scroll compressor work? So this is just a video of it. So this is what you'll see inside your
Compressor
unit.
is also known as a scroll pump and consists of a shell with an in and an
No
outlet.
video. No video.
No video. You can't, you gotta pull in and out of stuff.
Okay, sorry.
And that's why I didn't show videos last week, because it's
No, there is a trick to this,
yeah,
and
Tony knows how to do it. I still don't know how to do it.
hold on a second.
Yeah, it's something you have to get into before you open your
Well, you gotta switch in and
your
out.
whole program to do your select.
Yeah, I should have done this beforehand.
I think if
It's kind of interesting. I'll pass this along. You can take a look at it. It's at least in my opinion.
I think if you just stop share and then open up the video as a share. Go to your desktop. You'll have both,
Maybe you're right.
have-
I think you're right.
You'll
I
have
think you're
both
right.
of them there. You'll have both things
Nope,
on your
you're right.
desktop.
You're right.
So stop one, start the other.
Yep. Nope.
And
I know exactly what you're saying. Yep.
They're both down there.
Yep.
So start share again. Or share screen. Little green. There you go.
So let's see if this works.
Which is used, for example,
Can you
to
see it now?
the plain
No,
bearings.
yeah, there you go. There you go. We're on a roll.
Which is found in the upper part of the shell in motion.
So I'm going to start it over again.
A scroll compressor is also known as a scroll pump and consists of a shell with an in and an outlet. The lower part of the shell contains the lubricant, which is used, for example, to lubricate the plain bearings. A motor sets an Archimedean scroll, which is found in the upper part of the shell, in motion. The scroll housing has an inlet, as well as a discharge port and a fixed scroll. Here, the scroll housing is made transparent. The scroll housing has a base plate. The fixed scroll is attached to the underside of this base plate. For better visibility, only the moving scroll with its base plate and the fixed scroll are now being displayed. Gas is absorbed in the forming chambers and transported to the center of the scroll set. As the rotation progresses, the chambers become much smaller, so that the gas is compressed within the compressor. Therefore, this type of compression is called internal compression. In the middle of the scroll housing, which is shown here in green, is a discharge port through which the compressed gas can escape. Normally, there is also a check valve. Today, there are several compressor designs. On the one hand, the movable scroll can move with an extremely small distance to the other scroll. The scrolls therefore do not touch each other. On the other hand, there are also designs in which the scrolls are in contact. Such scroll compressors usually have a better seal, and thus, a higher efficiency. Axial sealing can also be designed in various ways. One possibility is the use of floating tip seal. These are present on both scrolls and are pressed against the base plates by gas pressure. In this animation, the upper base plate is not shown. Scroll compressors are used in air conditioning systems and heat pumps. When used in cars, they are known as scroll-type superchargers. The small number of moving components results in a high level of operational reliability. Due to their special design, scroll compressors are also highly efficient. In addition, noise emission of scroll compressors is quite low.
Okay, so I'm gonna,
One thing you need to do before buying anything online. Don't spend another dime
Oh,
on
hold on a
Amazon
second.
until you watch this first. Watch this. I can show you how to get the sweetest deals online when you shop from major retailers.
I have to get rid of this. Hold on just a second. Oh, man. Oh, here it is. Okay. Let me get back to my presentation here. I have another one of these that I think is perhaps it's a little bit different, but maybe better. I'm gonna share this other one as well.
So how did the old compressors work? Did they have like a, compression cylinder kind of thing, like an ice engine, or I like the old ones that they'd have in the bowels of the chemistry buildings, right? That were really, really loud. How did those work?
Like a
So, sorry, go ahead.
like a piston, so to speak.
Yeah, there are various various designs, I think, Lee. And I know that they're at least, really, boy, it would be interesting actually to go to the cogeneration facility in Madison, because they have a big cooling unit there. And I don't know at that size what design compressor they use. And you can actually go to multi-stage compressors as well. In fact, there's some discussion about that here.
Mhm.
But I know that certainly I'm going to guess hey you could use really tight screw compressor. You could use I wouldn't think a gear pump oriented compressor would necessarily be appropriate, but definitely a piston would be, right?
Mhm. Yeah, that's what I was thinking, maybe.
Yeah, and I think that certainly pistons used to be used, but I don't think in air conditioners. I don't think in a residential air conditioning unit you would ever see one. I don't believe so. But what's kind of interesting about these to me is that, and the reason I got into looking at them is because I realized that depending on outdoor air temperature, the suction conditions of this heat pump change. Okay, so if the incoming pressure is too high to this thing, remember that this thing works in a constant pressure ratio. So if the incoming pressure is too high, or is higher, then the discharge pressure is going to be very high. And there's a limit as to what the discharge pressure can be in these things, because if it's too high, you'll exceed the maximum working pressure of the system, and you'll see a failure. And so generally there would be some sort of pressure relief device or something like that would prevent the damage that would occur then. And so I was very interested in how this thing was designed. And my understanding is that this scroll compressor, at least some of these, have springs at the top of them. You saw where the discharge was, and how that there's a plate at the top. And my understanding is that with some of these, that if the pressure exceeds some maximum level, that there's a spring that then will compress and create a space that results in relief of the pressure back to suction somehow. Okay, and that actually
Relief valve, emergency relief valve at the top.
effectively, but I believe that they've designed this more cleverly than that to improve performance and efficiency. Okay, yeah, I just thought it would be something interesting.
Could I just remind you that it's almost 11 o'clock?
Okay.
Just so we can deal with some of the questions and things.
Sure. Okay, so let me go back. Let me reshare this thing. Let's go back here. I'm going to move through the rest of it pretty quickly, I think. Okay. So let's go back down to here. So that's all, the theory of operation and all that. So what I wanted to get into now is some of the improvements that have been made to heat pumps that have allowed them to operate in colder climates and be more efficient. And then, some of our experience with the one that we installed up here up north, some of the financial aspects of this, so the economic aspects, and then maybe a couple of closing and some alternatives as well. So these things were invented back in the 1850s, but the compressors that we use today are simpler to manufacture. You just got a little picture of that scroll compressor. That scroll compressor can actually be designed to operate on a variable speed, with a variable speed motor. So you put an inverter upstream of that thing, and then you can control the amount of flow through this system to accommodate exactly what your heat and cooling loads might be, right? So that's obviously much more efficient. So the electric motors themselves, they're more efficient than what we used to use. We used to use just a single speed induction motor. These motors that are being used nowadays are much more efficient than those that were in place, say, 20 years ago. The controls that are incorporated into these systems are likewise much better. In particular, that metering, that valve that drops the pressure dramatically. It used to be, if you look at an older air conditioning unit in particular, you'll see a bunch of little capillary tubes that accomplish that pressure drop. Nowadays, what's used is called a temperature control valve, a TXV valve. You'll hear it referred to, and that valve actually controls the flow into the evaporator to be such that the outlet temperature of the evaporator is a little bit higher than the boiling temperature. Okay, so it picks up a little more heat than it dumps a little bit more heat. Let's see it. I guess the refrigerant picks up a little bit more heat than would be required to completely vaporize it. And so that valve actually causes the system to be much, much more efficient. It also creates a problem when you're let's say you have a minor leak in your system and you have to adjust the amount of refrigerant you have. It actually creates some complexity in refilling the system as well. And one of the last improvements to heat pumps has nothing to do with its operation. It has to do with these tax incentives that have been created by the Inflation Reduction Act, the IRA, to install heat pumps, in particular higher efficiency heat pump systems. So it used to be that a heat pump, it was limited to regions of the country where the lowest temperatures encountered were in the 40 to 50 degree Fahrenheit range. Okay, so essentially the southern part of the United States, it was very appropriate to have a heat pump installed. But units today, they really can effectively deliver heat when the outdoor temperatures dip way into the negative numbers, actually. I know we up here, I've operated the one up here at somewhere between -10 and -20 degrees Fahrenheit. Now that it does affect the efficiency of the unit. It affects that coefficient of performance. Again, if we go back, one second. We go back to this diagram. If that outdoor temperature is much lower, then we've got to drop the pressure quite a bit more. That means that we're going to put more energy in to go from this lower pressure to back up here. Okay, so we're going to have to put more energy in to get this thing to operate like this, and so our coefficient of performance is going to drop as a result of that.
Question.
Okay. Yeah, sure. Go ahead.
Do you have any backup for this, or is this your sole form of heating in the wintertime?
No, we do have backup, and I'm going to mention that in just a second. Okay, because it's important. It's one of the important, in my opinion, one of the financial considerations. Okay, so to give you an idea of how this thing operates in the winter, this was our unit last winter. Okay, and I actually had gotten. You'll notice I put a little roof over top of it, and I did that to try to avoid the problem that you see here, which is snow accumulating around it. because just like your air conditioner at home, this thing is sucking air in from outside and it's exhausting it straight up. And so, it's important that the sides of it are exposed to air instead of snow. And, our snowfall got pretty heavy up here after a while. And we were not necessarily up here all the time. So we had to actually have somebody come over and shovel this out a little bit. But you also notice, and this goes to your question earlier, Richard, this frost building up on the outside now this is the outside, in this case, this is the evaporator, okay, because it's a heat pump. You'll notice that frost is building up on the heat exchanger. And that's a problem. And so these units also go through a defrost cycle. In spite of the fact that it's very cold and the humidity is very low, you're operating this thing very cold relative to the freezing point of water. And so you're condensing water, and then it frosts, and every so often this thing will reverse, and you'll actually hear it. You'll hear that four-way valve reverse, and then heat those coils so as to melt the frost, and it drips off, vaporizes, and then you start the cycle all over again. And this is a source of inefficiency. Okay, the fact that you have to do this with a heat pump, and you generally don't do it with an air conditioning unit. Okay, does that make sense, Richard?
Yes, it does. Thank you. How long would this unit take to pay for itself for getting any federal subsidies, roughly?
So I'm going to get into that a little bit.
Okay.
Okay.
Yep.
Okay. So I was very interested in the performance of this thing. In fact, from a control point of view, I wanted to know, hey, we have our backup system up here is forced air propane. Okay, so we had installed for many years a high efficiency propane fired furnace, and I wanted to know, hey, when should I switch from running the heat pump to using propane from a financial standpoint? And so I was curious about the coefficient of performance and how it changed as the outside temperature changes. Okay, and it turns out that it also depends on what your backup is. Is your backup propane? Is your backup natural gas? Or is your backup electric resistance heat right now? Okay, it depends on the prices of those things and the efficiency of your furnace and that sort of thing, as to how to operate this heat pump. So this was my this was my first go at this, at trying to figure this out. This was my estimate of the coefficient of performance and the operation, of the heat pump as the outside temperature dropped, and notice that the outside temperature is dropping going to the right as opposed to the left. And essentially this top line is the heat pump. Okay, that's its performance. This top line was essentially natural gas. This was essentially the cost of running our natural gas fired boiler in Madison. This blue line was the cost of running our propane fired high efficiency furnace in up in northern Wisconsin. And the lowest line is the cost. It's actually not just the cost, it's actually the output per dollar of electrical resistance.
Wow.
So you can see, well, I didn't really do this correctly. I should have redone these graphs, but electrical resistance is clearly a non-winner pretty much all the time here. And so the only time you do it is when you don't have sufficient capacity in your heat pump to properly warm your living space. In this case, actually, we could get down, based on my original calculations, down to minus 40 degrees outside, and I would still rather run my heat pump as opposed to switching to backup. Turns out we wouldn't have enough capacity, but be that as it may, I would still prefer doing that. And then, as the cost or the cost of the energy goes down, then that changes. Okay, so it turns out that my calculations didn't match at least what's been published, although I don't know really where or how these numbers were derived. But this is perhaps a more conservative analysis of a heat pump that probably reflects a bunch of the inefficiencies. For example, probably reflects the fact that you have to reverse the cycle and defrost every once in a while, as an example. And in this case, it turns out, again, electrical resistance is rarely desired. You would do it only when you didn't have sufficient capacity. But in this case, natural gas, you would switch somewhere in the 35 to 40 degree range. It would become you would become indifferent as to which of those two, whether you use the heat pump or natural gas. But over here, down around 5 to 10 degrees, maybe 0 degrees, it would behoove us up here in the where we're using propane to continue to use our heat pump all the way down to 0 degrees Fahrenheit. Okay. Yeah. So again, this actually changes every year as the price of propane and natural gas change, and electricity for that matter.
Got another quick question.
Sure.
I was working with the International Crane Foundation about 20 years ago, and they decided to take a part of one of their buildings and to hook up a heat pump with coils of a liquid antifreeze and bury it underground so that they could use a constant temperature of somewhere in the neighborhood of 50 degrees or so year round. And they still did not have a very good success. Now, that was 20 years ago. But my question to you is, you haven't done that. You've just used outside air.
Yeah.
Do you think if you'd used coils, would it have helped any? It seems to me you wouldn't be using such a huge temperature difference.
Absolutely. And it's very possible that system wasn't installed properly. I mean, I'm going to comment on that here in just a second, Richard. And I can make guesses as to some of the problems that they may have encountered.
Now,
okay.
Now, how much do you think you would have improved your efficiency had you used these buried coils or even a well to get down to lower, more even year-round temperatures?
So what in fact happens is that, so you see here that your outside temperature has a significant effect on the coefficient of performance that you experience. Okay, so now imagine that the ground temperature that you're interchanging with is constant up here at 50.
Yeah.
Okay, well now you're operating up here. Okay. you're getting much more energy out per dollar that you're putting in. And that's why you go to a geothermal system. They are much more efficient. But if you don't design them properly, then you could actually end up cooling the ground around that geothermal heat exchanger to the point where it can't exchange heat anymore. So it's important that it be spread out enough that you have enough area. And in fact, there's one contractor I talked to down there. I actually sat in on a presentation at the Energy Institute, and I'm going to mention that if we have enough time. But it's one of the things that could have created a problem there if it wasn't designed properly. And I'll tell you that our experience up here has been that I'll say next to nobody here knows anything about heat pumps yet. I think actually, I won't say that I know as much as they do, but it's probably close, and that's kind of embarrassing, at least in my opinion.
Thank you. That helps a lot.
Doug, I'm wondering why those 3 horizontal lines aren't actually moving up, because I think the operating cost of a regular furnace, as the outside temperature goes down, your bill usually goes up, right? I mean,
No, that's right. But realize you have to take a look at the units on the vertical axis. That's kilowatt hours per dollar. That's the amount of energy that you are getting out per dollar that you're putting in. And so, okay, you have to put more kilowatt hours in, or you have to use more kilowatt hours to heat your home, but the kilowatt hours per dollar that you put in, that stays the same.
I see. Okay. Yeah,
Okay.
I understand. Yep.
Yeah, sorry, I didn't spend enough time explaining that, I guess. Okay, so the operating costs. So this is essentially summarizing what we just talked about. And effectively, electrical resistance heat, given that all you're worried about is dollars, you would typically not use your electrical resistance heat unless you don't have enough capacity in your heat pump to keep the house at temperature. Okay. And then for us, well, I'm going to get into that here in just a second. So so what did it cost us to install this thing? In our case, I mentioned earlier, we already had a high efficiency propane heating system, and actually air conditioning system as well. Okay, so we had the type of system that typically people have installed it around Madison. And it turned out, so we already had an indoor air handler. Okay. And so when what happened here was that our air conditioner started to leak refrigerant. And we dealt with that for a few years until it just really wouldn't hold charge anymore. And so we decided that we were going to replace that air conditioner, that what's called the condensing unit, outdoor unit, for this system. And that outdoor unit, as an air conditioner, probably would have cost us about $4,000. By changing the specification to include a heat pump, it cost us about $5,000. Maybe it would have been $3,000. I don't know exactly what it would have been, but it probably been somewhere between $3,000 and $4,000 to replace the air conditioner, and then another somewhere between probably $1,500 to $2,000 to upgrade that to a heat pump. Okay, all in all, it costs us about $5,000 to install this heat pump up here. But But given that we were going to replace the air conditioner anyway, our net cost for the heat pump part of it was probably somewhere in the $1,500 to $2,000 range. A new system, including the air handler, I think would cost $7,000 to $8,000, but it depends on what you buy. So it turns out that like anything, you can buy Cadillac systems versus less expensive systems. Up here, this is not we don't live up here all the time, so we never thought that it was justified to put in a gold-plated system. But I've heard a friend of mine told me that I think he paid somewhere between $15,000 and $20,000 for a system. But what he put in has all the bells and whistles in it. So, you can put a lot of money into one of these things, and in my opinion, you have to justify each incremental part of the investment. Okay, so to get that extra efficiency, you may have to pay a lot, and so then the question is, does that make sense? And my financial background told me at the time, no. And you should all know that I'm a fiscal conservative, also known as a cheapskate, and so we didn't put in the top of the line system, but I'm going to give you an idea as to what it costs us to run this thing now too. So if you're doing it yourself, if you're considering installing one of these things, I recommend, from our experience, trying to find a contractor who has had some experience installing these, because my experience up here was that, in fact, we were told that I think the guy we ultimately had install this said that he hadn't installed one of these things for 5 years. Now, I expect that in the next few years, he's going to install a bunch of them, but they had trouble actually getting the controls to work properly. And in fact, the installer didn't hook it up correctly, and another person had to come back in and flip a few switches in the air handler to get it to work properly. So find a contractor who's installed one of these things before, and then talk to some people with whom that person has worked. Just a recommendation from me, anyway.
Thank you.
There are, in my opinion, questions about the durability of these things. So first of all, one of my concerns was the refrigerant they were going to use. So this heat pump that we've installed has R410A in it. R410A is a hydrofluorocarbon. It actually will become it won't be allowed to be used after, it's either next year or the year after. So no new units will be allowed to use it as a refrigerant. And I was concerned about that because my experience with air conditioning units is that they leak.
Yeah, well, yeah.
And eventually you're gonna have to put some more refrigerant in them, and if the refrigerant becomes less available, it becomes more expensive. Our old system had R22 in it. R22 is a chlorofluorocarbon that is now banned under the Montreal Protocol. No longer manufactured, to my knowledge, except where it is used as an intermediate. It turns out that we happen to have some because my father-in-law was an HVAC contractor, but it's no longer used, and neither is R12. the refrigerant that used to be in all cars, for example. These have been replaced with hydrofluorocarbons, and they are generally speaking going out of favor, and they're going to be replaced. My understanding is that carbon dioxide is likely to be, it's certainly going to be one of the alternatives. And there are some others that are being considered, but the others potentially could be flammable, and that's a safety issue. So that's one of the considerations. Okay, if you're going to get one of these, find out what refrigerant is going to be installed and whether that refrigerant will be available going into the future. Let's see. Another thing that happens is that these, in particular, that evaporator coil gets pretty cold, and then it goes through these in particular, you switch it around, it becomes a dense coil. It sees fairly significant temperature swings, and that can cause problems in the welds, which result in leaks. And a leaking system has to be fixed, and it's hard to, first of all, it's hard to find the leak, and then you have to weld the joints back, and that's all expensive. So it's a concern that I have. It remains to be seen what the long-term durability of these systems is. I don't know. Everybody will tell you they last 10 to 15 years. I think they all last longer than that, just by personal opinion. Again, because I'm a cheapskate. Finally, Richard, geothermal systems would seem to be potentially more durable. And that's in part, at least, because certainly the outside part of it is going to be held at constant temperature. That heat exchanger is actually plastic tubing, and much less likely to leak over a long period of time. And not only that, but the entire unit, everything that's a moving part in that unit will sit inside, as opposed to having half the system outside and half the system inside. The compressor actually will be inside the home. And so you don't have to move refrigerant as far. And there's oil that's mixed in with that refrigerant that has to transfer with it. And you don't have the likelihood that oil will separate and end up somewhere away from where it belongs, which is at the bottom of the compressor, lubricating those bearings. And this was actually mentioned to me by a practitioner, an HVAC guy who installs these geothermal systems. And he mentioned that they're likely to be much more durable because the whole system is sitting inside, protected from the elements.
That's very helpful. I really appreciate you.
So our motivation to change. First of all, one of the reasons that I thought about this right off the bat was because, everybody knows I talk about this incessantly, about the climate problem that I've been working with. Actually, this course exposed me to the problem. I'm much more knowledgeable because of it. And I expect that we're going to have to transition from fossil fuels. We're using fossil fuels. We're using them up here in the form of propane. And then there are financial incentives that have been created through this Inflation Reduction Act, the IRA. And finally, I expect, and I'm going to give you my experience up here, that we would experience lower costs using a heat pump than we would using propane. So that's what motivated us really to do this. This place up here is now a little bit more than 30 years old. As I mentioned, it's propane forced air. It was that propane forced air furnace was replaced in 2014. The central air conditioning unit, though, was about 30 years old. So that condensing unit that sits outside was about 30 years old, and it was losing its refrigerant charge, needed to be replaced, both because the refrigerant is now banned, and because fixing the leak would be more expensive than was justified. So we were going to have to bite the bullet anyway. Why not get a heat pump at the same time as replacing the air conditioning unit? And as I mentioned, the costs are actually very comparable. And the IRA incentivizes electrifying everything, really everything, because we know, certainly, we've all been talking about this with respect to electric vehicles. Electric motors are inherently much more efficient than internal combustion engines, and for the most part, heat engines in general. So one opportunity for electrification is residential and commercial heating. Simple space heater, which relies on generating heat. You could do it that way, but that's much more expensive than using the heat pump. And I've tried to show you why that is. So again, how do you do it yourself? Find a good contractor. And it turns out that actually, and get more than one quote, because we actually saw quote prices normally vary somewhere around $1,000, and we got 3 different quotes, and we saw that kind of variation in the quotes that we got. And also look at each step up in efficiency of the system as a different financial benefits to justify it. As I mentioned, that additional, you can buy gold-plated systems, but the question, at least in my mind, is whether economically those step ups are justified right now, given their costs. And I also I have this link down here. I'm not going to. But Focus on Energy actually has a very, in my opinion, a very good buying guide for heat pumps. And I'll send this presentation out. And I would suggest that anybody who is interested in heat pumps and buying one, installing one, take a look at this kind of buying guide from Focus on Energy. In my opinion, it looks pretty good. Sorry?
I was just going to, I didn't want to cut you off. I was just going to read out a comment. Are you ready for that?
Sure, go ahead. Sure.
Steve Shellen says his few concerns about geothermal systems, specifically, says plastic is a poor conductor regarding extraction of the energy from the ground.
That's correct. However, that doesn't mean you can't put a lot of it down in the ground. And it turns out, I can't remember. I'm going to get into this just a second, but I can do it right now. I actually listened to a presentation at the Energy Institute specifically about geothermal systems. And I was going to get into this in a little bit, but you guys may know this. Turns out that EPIC has, I believe, the world's largest geothermal heat pump system, and as well as air conditioning system. They have drilled somewhere in the neighborhood of 3,000 wells on that property, and I think they're going to be drilling more. That all exchange heat with the ground, they exchange heat with the ground. They use it both for air conditioning as well as heating. It turns out that commercial buildings need a lot more air conditioning than they need heating. So they're actually cooling their buildings much more than heating them, except in the dead of winter. And they've studied this. They studied this to death, in particular because they have elaborated with a professor. Turns out that he's I believe he's a civil engineering professor at UW. His name is, I believe his last name is Tingen. And if I can find it, I'll find a link to his presentation. Very, very interesting. He's collecting all kinds of data on this system. There are all sorts of opportunities for optimization. And he in particular mentioned that actually running both the system in both heating and cooling mode is important to ultimately even out the ground temperatures where this heat exchange is taking place. Because as you're extracting heat or you're dumping heat over long periods of time, you affect those ground temperatures and then you affect the heat transfer. Another guy, in fact, I think it was him, who mentioned to me that roughly speaking, these are some numbers that you can keep in mind. A single well, assuming that in a geothermal system, you have to dig wells as opposed to trenches. A single well, something like about, I think it's about 250 feet deep, costs about $5,000. Okay, and a single well will get you about a ton of let's call it refrigeration. Okay, so if you consider that most people in their houses have somewhere between 2 and 4 ton units, depending on the size of your house, it gives you an idea as to what a geothermal system. In addition to the equipment, those wells are relatively expensive. Okay, so about $5,000 per ton of refrigeration. Okay. So nowadays, we have these subsidies through the IRA. It includes the installation of the heat pump. The subsidy itself depends on your level of income, as well as the efficiency of the system that you buy. And another important aspect of it is that the rebate itself is applied directly to the purchase price, as opposed to just being a tax subsidy. So you'll see the benefit, the reduction in cost immediately, as opposed to having to wait until somewhere between February and May of the next year. Okay.
Yeah, there is a couple more comments coming in from Steve Schellen. He says you need a subsurface that can be drilled and not rocky or limestone for the geothermal aspect, and you need to be located spaced between buildings, so not nearly as useful in a commercial business area like a city.
Again, I would suggest, and I'm not an expert on this, but I know that the work that these guys at UW, this Professor Tingen, as well as EPIC, the work that they're doing, they are actually developing methods to estimate heat transfer depending on soil composition. And I don't know what they drilled through. It's very possible they could have drilled through rock, and you can drill through anything. It just costs you more, and you'll get different heat transfer characteristics. So I'm not in a position to comment on what the limitations are, but there is a guy who actually his business is out of Cambridge, and I spoke to him after this presentation at the Energy Institute, about this, and he's extremely knowledgeable of this, and actually before they design a system, they actually drill a pilot well to determine exactly what needs to be put in place to get your system to work properly.
Yeah, Steve says that he has a commercial building with 13 separate AC units and a high level of limestone. The area has limestone surface mining. So yeah, you definitely can go through the limestone. So it varies, as you say, depending on the material and proximity of other buildings and so on.
And actually, if you have a large pond, it's even better, it turns out. So there are lots of different options here. Again, I'm not an expert at it. I'm not going to go through all the options, but I've learned and I've learned a lot about it, and I've listened to a bunch of people talk about it. I actually, at this point, I know certain people that I would definitely go talk to about this. In particular, this guy at UW, this professor in the civil engineering department, because
I think your slides reflect that. Doug, I really like your I'm not enough of an engineer to appreciate some of the Moliere aspects, but your concluding slides are very well thought out and very, I think, honest and balanced, and I appreciate that.
Okay, so other applications. So it turns out that this heat pump, it can deliver hot water in your house. Okay, so instead of interchanging with the outdoors, you can interchange with your indoors, and you can discharge that compressor and the refrigerant from the compressor into a hot water tank and heat your hot water. And in fact, these things are commercially available now for residential applications. And what's kind of interesting about them is that the flip side of the evaporator coil that sits outside that sits inside the house then becomes your dehumidifier. So you cure two problems with one machine, turns out. And these things are, as I said, they're available now. I think that the other day, we heard about using heat pump in cars now, in particular electric vehicles. I think now, I think we should all understand exactly why that is. They're much more efficient than heating directly with electric resistance heat, unless that electric resistance is right underneath your butt. Also, and especially for commercial installations, you can consider geothermal systems, and we talked about that because they have a tendency to be much more efficient because the ground at depth tends to be at an ideal temperature for the heat pump operation. And here's where I'm mentioning that $5,000 per 250-foot well. It's about 1 ton of refrigeration. Michelle and I, this is a couple of months ago now, maybe about a couple of months ago, actually went up to Alaska. It was my 50th state. One of the things that I was very interested in spite of my climate concern, was seeing the Alaska oil pipeline. I've heard about it for so many years, and I've really been interested in it. And we actually followed it up north of Fairbanks. So we actually went from north of Fairbanks all the way down to Valdez, not all the way up to Prudhoe Bay. One of the interesting things, aspects of the Alaska oil pipeline was, and this is a picture of it. Sorry?
The heat radiators.
Exactly. They, whoops, hold on.
You got it there.
Here it is. So it turns out that along the Alaska pipeline, there's a problem with permafrost. and the oil in the pipeline is hot. Turns out that it radiates heat towards the ground, and there is a significant concern during design that enough of that permafrost would melt to the point where the support for the pipeline would be in question. And so what they did was to design these essentially a passive heat pumps all along the pipeline, wherever this thing is elevated, and even where it's not elevated, even where it's buried, you'll see these things. So these radiators here are actually pipes that go down into the permafrost. They are charged with ammonia. And in the dead of winter, when the temperature outside is around -40 or so, these things act as heat pumps. So the outdoor temperature is now, let me think how it works now. So the outdoor temperature now is below, let's see, it's below the temperature of the vaporized ammonia. And so it radiates heat to the outside. And then that then pulls heat from down in the permafrost layer. So literally what's happening is that this the permafrost is boiling the liquid ammonia. The liquid ammonia the vaporized ammonia rises to outside, discharges heat outside and condenses, and then drops right back down to the bottom. In the summertime, it doesn't work. So during the winter, it turns out that the permafrost is sort of recharged along the pipeline to prevent that problem from occurring. And we learned about this as we were, listening to people talking about it, I think. And I thought it was sort of serendipitous that I had heard about it right before doing this presentation.
Yeah.
I was there this summer.
Oh.
And went up the Hall Road to the Arctic Circle and saw a lot of this. And
we must have been on the very same excursion that you went on, because we flew up and then drove back, I think it was.
Well, you can land at the on the Hall Road, and we had a couple of Cessna 175s at the Arctic Circle point that we stopped.
Yeah.
It's a self-dynamic radiator system.
Right. It's passive. It's the way I would describe it. It's passive. So I couldn't do a talk like this without talking about carbon pricing. And so I had to mention this for everybody's enjoyment, I guess. Many of you know that I work with Citizens Climate Lobby. I've been pushing for carbon pricing for some time. I believe that it's the most effective way of dealing with climate. And one of my concerns going into this was that I also mentioned to you, I'm a fiscal conservative. I'm a cheapskate, and I'm concerned that if a carbon price is put in place, that not only natural gas, not only oil, but propane is going to become more expensive. And as it becomes more expensive, alternatives will be preferred, and it will drive that efficiency curve that I showed you to the point where I won't want to use propane anymore. In fact, it's very likely that under those circumstances, you would prefer to use electric resistance heating, depending on how big a carbon price is put in place. And so I sort of factored that into the decision to install a heat pump. And the last number that I'll throw at you, I only really have 1 year, really probably less than a year of experience using this heat pump. I believe that last year, we saved somewhere between, we will save somewhere between $200 to $400 a year in heating cost up here using this heat pump. And I say that based on some average numbers of what it's cost us in the past and what our experience was last year. And so if I compare that to what I believe to be somewhere between $1,500 and $2,000 that we paid for it, we'll get somewhere between let's say a 4 to 10 year payout on the money that we've invested in this without any carbon pricing at all. If carbon pricing was to go into place, this would be just a slam dunk. And my guess is that that was with no tax incentive either. Okay, so we installed this at a time before tax incentives were available, or IRA incentives were available. So with that, I will stop my share and I'll be done.
Great. Any other thoughts, questions, contributions? You've got.
Well, I would say that if we get carbon pricing costs in there, that says we need nuclear power to generate the electricity to run these heat pumps. If I can get my ad in.
Right. Stephen used to work at Point Beach.
No, that explains that.
Pardon?
I say that explains that there's no.
He's a member of our Friends of Fishing group.
There's no bias in that statement whatsoever.
No.
Oh, definitely a bias.
Sure.
A bias can also mean that you know more than somebody else about something.
That's true.
I think one point to make about the incentives for heat pumps, I think that you need to have a cold climate heat pump rating, so not just the regular heat pumps.
I think that most of them are cold, or I'm going to say that most of them are cold climate oriented now.
And I've done a little investigation because I would like to install probably, well, ideally we have a boiler heating system, so we don't have forced air. And so to air condition our house, we have, window units, which become not much fun to install and take out each year. And so putting in mini splits, and I'm just, ideally what I'd like to do is to eliminate our gas boiler entirely and heat our home just with the mini splits, and then produce our electricity with our solar panels. And I'm just wondering if you have any thoughts on the feasibility of that.
So it turns out that we actually we're in a similar situation to you in Madison. Our house is heated with a boiler, steam boiler, and it turns out that one of the previous owners had actually installed an air conditioning system in it using what are called high velocity it's a high velocity system. It has ductwork that is probably, I'm going to say it's 3 inches in diameter as opposed to normal like 8 inches, something like that, or whatever you normally see in a brand new house. So we actually do have an air handler. It's up in the attic, and we have an older outside, air to air condensing unit. And I've thought about putting the heat pump in, but our air conditioner has not failed yet. So the justification isn't as obvious. I mean, this is the economic side of it. You can justify this on many different levels. So if you're really worried about climate change, then you can certainly justify it just based on that, right? But if you just look at economics, it takes more to replace your outside, takes more justification to replace your outside unit if it's still working. Having said that, I know our next door neighbor is in exactly the same position as you. She installed a mini split. She has 2 indoor, I'll call them distributors. I don't know what they actually call them in the HVAC world, but it's being distributed in 2 different places, and that's what she air conditions her house with now. One on the lower level, one on the upper level. So it's very feasible. It won't be perfectly distributed, and then what you have is a system that can operate as a heat pump, but also you have a backup. You have your existing backup, which is cheaper than at least at the moment. It's cheaper to operate than electrical resistance. Okay, which is what you'll get if you put in a brand new system and you have to put in a forced air system or something like that. Which is really hard to shoehorn into your house. So that's what I know about it.
I think it's a tragedy to use electrical resistance. It's such a terrible way to convert from electricity to heat.
But if imagine if you're, I'll just throw something out. You're generating electricity with a I don't care what it is. It could be your solar panels, and you have a flow battery in your house somewhere, where you store that power when you're not using it. And okay, you're getting the electricity for free, and you're just using it for heat as opposed to something else.
That's true.
Well,
so I think we're.
What is
What
is a mini split? I don't know what that.
Yeah, what is a mini split?
Well, Jeff, you can explain it if you want to.
Well, I think it's I forget there's a unit outside which is that your compressor outside? And
it's what they typically call the condensing unit, and it has a compressor in it. Yep.
And then on the inside of your house, you put up on your wall is the mini split portion, which is where the air comes, where the air gets, I forget the.
So
circulator.
I'll explain what you're doing. So outside you're doing all the same things that you see in a regular system. Inside, what you do is you distribute the refrigerant to different indoor units. Okay, and it's actually metered to these different units. One in the case of our neighbor, one upstairs, one downstairs, and then each of those units cools or heats either way. Okay, but they have to both do the same thing. Because you only have one compressor outside and it would be, you only have one heat exchanger outside, actually. That's what the big problem. Okay, so that's what the mini split is. You're splitting that flow of refrigerant to different places.
Thank you. Glad to have that clarified. I think we should wrap it up. We're going to talk next week about geothermal energy of a different sort, where we're converting the Earth's interior heat to electricity mostly, and we're going to focus mostly on upgrading it. What's the future potential, as well as some of the history, and there's an awful lot. It covers it globally, so it makes it interesting. It's a fascinating subject when you think of it globally, rather than just in the United States. So look forward to seeing you next week. Meanwhile, keep well. And
Very good program, Doug.
yes, it was.
Sure.
Doug. Appreciate that very much.
Yeah, my farm just south of where I live here has limestone that protrudes from the ground. We built a garage simply by scraping the dirt off, pouring concrete on it, and building the garage. And that was oil heat.
Yeah.
Okay. Very good.
Okay.
See you all next time. Have a good week.
Thank you.
Thanks again.
Bye.
Doug, very nice. Bye-bye.
Sure.